Welcome and thank you for attending our webinar on selecting the right high-density relay for your PLC, DCS, or controller discrete I/O card. Keith Ingram is the International Sales Manager at Acromag, and he will be presenting today. My name is Karen and I'm your moderator. We'll begin in just a minute, but first I'd like to remind everyone that during the presentation everyone will be in the mute mode, so if you have a question for Keith, please use the questions section in your control panel. Before we get started, let's start with a poll question here, and our first one should be on your screen now. What industry are you in? Please select one. That'll give us an idea where we're going here. And I'll give you a couple seconds to fill that out, and then everyone will see the results. Okay, it looks like everybody's finished. Let's close the poll, and we'll share it with everyone. And okay, that's interesting. Other factory automation, that's good. Okay, now turning over, we'll start the presentation. Keith, turning it over to you, Keith.
Okay, thank you, Karen. Welcome to Acromag's webinar on the XTA-MRNO-6 mechanical relay output module. My name is Keith Ingram, one of the regional sales managers for the Process Control Division. Thank you for joining us. Okay, let's get started. Today we will talk about the following topics: a brief history on the electromechanical relay, two types of a modern electric relay, electromechanical relays and how they work, solid-state relays and how they work, relay logic versus PLC logic, the MTA-MRNO-06 features and benefits, summary of the XTA-MRNO-6, and also on the XTA-120V-6 optical input module. Joseph Henry was an American scientist who developed the electromagnet into a practical device. He invented a precursor to the electric doorbell in 1831 and an electric relay in 1835. The International System for Units of Inductance, the Henry, is named in his honor. In electronics, induction is the property of a conductor by which a change in current in the conductors induces a voltage in both the conductor itself and in any nearby conductors. We see this property used in electromechanical relays and transformers. Henry's work on the electromechanical relay was the basis of the practical electrical telegraph. Here we see a sketch of the Henry magnet and a surviving electromagnet, which he termed quantity magnet. The first relays were used in long-distance telegraph circuits, repeating the signal coming in from one circuit and retransmitting it to another. Relays were also used in telephone exchange in early computers. A relay is an electrical operated switch. Relays are used when it is necessary to control a circuit with a low power signal or where several circuits may be controlled by one signal. Here we see two examples of the modern electric relay. A solid-state relay is shown on the left side and a latching electromechanical relay on the right. Relays are used in controlling a high voltage circuit with a low voltage signal, as in some types of audio amplifiers. Controlling a high current circuit with a low current circuit, as in the starter solenoid of an automobile. Detecting and isolating faults on transmission and distribution lines by opening and closing circuit breakers, isolating the controlling circuit from the control circuit when the two are at different potentials, and in logical functions. For an example, the Boolean AND function is realized by connecting several normally open relay contacts in series. the OR function by connecting several normally open contacts in parallel. Here we see a latch and relay is used as an AND function. If the two push-button contacts are energized, then the relay coil will also be energized. When the off/break push button is pressed, the circuit becomes de-energized. These types of circuits were used to logically control a process into the development of the PLC in 1968. Now Karen has another poll question for you. Karen?
Oh, yes. We have another poll question for you. It's which of the following relays have you used? And please select one: solid-state relays, mechanical relays, both solid-state mechanical relays, or I don't use relays. And I'll give you just a couple more seconds to make your selection. Okay, let's close the poll and let's see the results. Looks like most everyone uses both solid-state and mechanical relays. That's good. And now back to you, Keith.
Thank you, Karen. Heavy-duty relays are used in the industry to do the heavy lifting, like controlling electric motors, clutches, valves, and contactors. Here we have two examples of a heavy-duty relay. A latching relay is shown on the left, and a three-phase motor starter is shown on the right. Here is an example of a compressor's clutch being controlled by a lower power relay. Karen has another poll question at this time. Karen?
Yes. Sorry, Keith. I had myself muted there. Which of the following devices have you used? This is our third poll question, and I'll give you a couple minutes to make your selection. Okay, let's close that one and share the results with everyone here. And I hope you find these poll questions interesting by some of the answers. And oh, look at there, contact doors and electric motor starters and valves. Okay, Keith.
Okay, thank you, Karen. A solid-state relay is an electronic switching device in which a small control signal controls a larger load, either current or voltage. It consists of the following: a sensor which responds to a control signal input, a solid-state switching device which switches power to the load, a coupling mechanism to enable the control signal to actuate the switch without mechanical parts. The relay may be designed to switch either AC or DC to the load. It serves the same function as an electromechanical relay, but has no moving parts. Every solid-state device has a small voltage drop across it. This voltage drop limits the amount of current a given solid-state relay can handle. Solid-state relays rated to handle as much as 1200 amps are available. Compared to electromechanical relays, a solid-state relay can be falsely triggered by transients or damaged by EMP. An electromagnetic pulse is a relatively short burst of electromagnetism. Its shortness means that it will always be spread over a range of frequencies. Here are some of the drawbacks of a solid-state relay. When closed, the solid-state relay has a higher resistance than an electromechanical relay and will generate heat and electrical noise. When open, the solid-state relay has lower resistance, which develops reverse leakage current, typically in the microamps range. Now, electromechanical relay has a lower ohmic resistance. When the mechanical switch is closed, it has very low resistance and a very high resistance when the contacts are open because of the air gap between them. Now, some types of solid-state relays have polarity-sensitive output circuitry, while electromechanical relays are not affected by polarity. Solid-state relays have a tendency to fail shorted on their outputs, while electromechanical relays tend to fail open. Many solid-state relays have optocoupling, which allows the control circuits to be electrically isolated from the load. In this slide, we see that a control voltage energizes an LED. The LED becomes illuminated and switches on a light-sensitive diode. The diode's current then turns on a back-to-back thyristor, SCR, or MOSFET to switch the load. Before the PLC, control sequencing and safety interlock logic was for manufacturing automobiles were mainly composed of relays, timers, and dedicated closed-loop controllers. Since these could number in the hundreds or even thousands, the process of updating these facilities for the yearly model changeover was very time-consuming and expensive. Electricians needed to individually rewire relays to change the logic. This was termed relay logic. In 1968, General Motors issued a request for an electronic replacement to hardwired relay logic. The winning proposal came from a company named Bedford Associates. After winning, the company started a new company dedicated to developing, manufacturing, and selling this new product named the Modicon, which stood for Modular Digital Controller. One of the people who worked on that project was Dick Morley, who is considered to be the father of the PLC. In this slide, we see a programmable logic controller controlling an AC motor. Since all of the machine control logic is created in the PLC, there is less relay hardwiring, saving time and space. A control panel which once was filled with relays to control a process is now replaced with a PLC and a limited number of relays. Now at this time, Karen has a couple more questions.
Yes, our final two poll questions here, Keith. The first one is a high-density design in a relay important to you? And if you could make a choice there, we have yes, no, and I'm not sure. I'll give you just a couple more seconds to make your selection. And okay, let's close this one and share it with everyone. And you can see here, most of you say yes, a high-density design is important in a relay, and 27% say you're not sure. So hopefully we'll answer that question, why you need a high-density relay, today. And our final poll question that we have today is saving panel space a deciding factor for your application? This is our final one, and if you could select one, please. It's yes, no, or I'm not sure. When we're done with these polls, I think Keith will be able to answer your questions. Okay, we'll give you just a couple more seconds here. And let's share our results. Okay, we have, I'm going to move this, 86% say yes, 5% say no, and we got 10% that say I'm not sure. Well, okay, so we're doing good. Thank you everyone for participating in our polls. Now Keith will continue on with the presentation.
Thank you, Karen. Now, over the last 45 years, PLCs have become smaller and distributed I/O has become more popular. remote I/O modules using networking protocols have helped distributed I/O grow, making commissioning a system quicker. As the cost of panel space increases, companies are looking for a high-density solution. Acromag has developed the XTA-MRNO-6 to partner up to our remote I/O modules or industrial PLCs. Here is a slide showing the new Busworks XT remote I/O module and two XTA-MRNO-6 modules, making this a very compact I/O solution. This unit is ideal for remote monitoring, distributed control, or SCADA applications. The XTA-MRNO-6 has the following key features and benefits. There are 6 channels of buffer digital inputs, which withstands DC logic voltages up to 32 volts, and it triggers on a 4-volt threshold. There are 6 individually isolated single-pole, single-throw, normally open mechanical relay contacts. The outputs switch both AC and DC with loads up to 250 volts and 30 volts, and with currents up to 5 amps. These are ideal for using with inductive loads and high-powered devices. The power supply input is from 12 to 32 volts. There's also 1500 volts isolation between the I/O channels and power. There is surge and transient protection on board, individual LEDs for each channel. It allows for both bus and rail power connectivity, which supports redundant power. It's also a high-density 22.5 millimeter wide package with pluggable front-facing terminals. There's a wide operating temperature range from a -40 to 80 degrees C. It withstands 25G shock and 4G vibration. It's CE compliant, UL/CUL Class 1 Div 2 Zone 2 approvals. It's pending right now, but they'll be coming out shortly. It's designed and manufactured with high quality and reliability using AS 9100 and ISO 9001. Here is a connection diagram of the XTA-MRNO-6 output modules. The power and inputs are wired on the bottom of the module, and the relay output are wired on top. Now I'm going to talk a little bit about resistive and inductive loads. In this slide, we see the difference between an inductive and a resistive load. Because the current lags the voltage in an inductive circuit, there is a back EMF. Generated when the circuit is open. Some types of resistive loads are lights and heater, where a coil would be an inductive load. In this one here, we're going to talk about a flyback diode to protect the switch in a DC circuit. In figure 1, the switch is closed and the inductor is fully charged. Current is flowing from the positive terminal of the voltage source to the negative terminal through the inductor. In figure 2, the switch is open and the inductor will attempt to resist the sudden drop of current by using its stored magnetic field energy to create its own voltage. An extremely large potential is created since no connection is physically made to allow current to continue to flow. The large potential difference can cause electrons to arc across the air gap of the open switch. In figure 3, a flyback diode solves this arcing problem by allowing the inductor to draw current from itself in a continuous loop until the energy is dissipated through losses in the wire, the diode, and the resistor. When the switch is closed, the diode is reverse biased against the power supply, and it looks like there doesn't have any, it's not existent in the circuit. When the switch is open, the diode becomes forward biased, allowing it to conduct current in a circular loop from the positive potential to the negative potential. The voltage across the inductor will merely be a function of the forward voltage drop of the flyback diode. The total time for dissipation can vary, but it will usually last for only a few milliseconds. In this slide, we see a RC Snubber network used in an AC powered circuit. It has the same function as the flyback diode, bleeding off the excessive energy through the RC network. Here we see how a typical digital output is connected to one of the inputs of the XTA-MRNO-6 module. This may be a digital output from one of our products like the Busworks Profinet DP, Modbus RTU, Modbus TCP/IP, Ethernet IP, or Profinet. Or it could be from an industrial PLC or SCADA controller. Notice that the inputs for the XTA-MRNO-6 is on the right-hand side. So what you would have is, for instance, the first input will be terminal 1, pin number 1, and then you would also connect to one of the returns. Designed as an interposing interface for safely driving high voltages and currents, AC or DC loads using the Busworks output module or other digital output devices like a PLC, it's used to control how high power devices like inductive loads, electrical motor starters, clutches, valves, contactors. It's also designed to save panel space and designed as a time saver. Now I'd like to talk a few minutes about the XTA-120V-6 optocoupler input module. The XTA-120V-6 utilizes 6 high-efficient optocouplers for sensing DC and AC levels on the input. The inputs are isolated from each other and from the power supply and outputs. Inputs support both DC and AC voltages. The input channels thresholds are designed to make monitoring AC main power convenient, with high to low and low to high thresholds at 90 volts and 60 volts AC, respectively. The 6 digital outputs are open drain MOSFET switches with a common source connection at the output terminal. This model provides low side syncing switching between the loads in return for DC voltage and current syncing applications. These units are ideal for remote monitoring, distributed control, or SCADA applications. Here is a connection diagram of the XTA-120V-6 optocoupler module. The inputs are wired on the bottom of the module, and the power and output wiring is on top. This slide shows the features and benefits of the XTA-120V-6 optocouplers. As you can see, they're very similar to the XTA-MRNO-6. We have the, again, we have a high density 22.5 package, our forward front facing terminals. We have the isolation between input and output, surge suppression. We can also do supports bus and rail power supply connection for redundant power. and again with the operating temperature and the shock and vibration rating. This concludes our presentation on the XTA-MRNO-6 high-density mechanical relay output modules and the XTA-120V-6 optocoupler input modules. Is there any questions?
Keith, I don't see any questions typed into the questions panel, so no, there are no questions right now.
Okay. Well, I'd like to conclude and thank you for joining us for this. If you have any questions, please either go to our website or call our group number at 248-295-0880 or email us at sales@acromag.com. Again, thank you for your time this morning.
Oh, Keith?
Yes.
Keith, it looks like there is a question from Tim. It takes him a little while to type in. He says, is there any, can you hear me?
I can hear you.
Is there any consideration for including a couple Form C relays?
For a what?
A couple Form C relays.
No, but I'll write that down and we can, I guess what I would do is if you were to email us that request, we can send it over to engineering and have them take a look at that.
Okay, and Benoit, I hope I pronounced that right, he wonders what the cycle time for mechanical relay is.
Hang on one second.
We have an okay.
Let me see. I'm looking up in the manual at this time. It says 20. It says 20 times per minute is the frequency on the mechanical relay. The response time is 5.25 milliseconds, typical.
Okay, and if there's any questions that we haven't answered, you can always send an email to Keith at